So as with the previous speakers, I'd like to thank Chris and Ann for the invitation to talk here. So what I'm going to talk today about is some simplified things that we've done looking at photoionization, where you can actually look at where the photoelectron goes in the molecular frame. And so in principle, I mean, when I was a graduate student ever so many years ago, 30 years ago, all the experimentalists could do, it had a polarized light, they'd have a randomly oriented sample and look where the photoelectron went relative to the polarization of the light. And so as you would calculate then, you'd fix the molecule, calculate the photoelectron in all sorts of directions, and do the orientation averaging. Okay, and so you'd get just one parameter that would describe the angular distribution of the photoelectrons for a given polarization of the light. So as experimentals, the intensity of the light they could use, the synchrotron source have improved, and coincidence measurements have occurred, then they could actually begin to look at, if I fixed the molecule in space and brought in linear polarized light, then you can measure where the photoelectron goes in the molecular frame. And so the question then becomes, what kind of things can you learn by doing that? So I'm going to talk a little bit about the general features. What do you expect in terms of these molecular frame angular distributions? I'll look a little bit about sort of the level of calculation, what kind of effects you see with more electron correlation in the calculation. Then many of these experiments, if you only have partial alignment, or if you're doing a coincidence measurement where you're depending upon the molecular fragment, there are other things that can occur. The system can bend, or it can rotate before the fragmentation occurs, and then you have to worry about the connection between what you calculate, a true molecular frame, and what they actually would measure. So in a dissociative photoionization experiment, they'd measure where the recoil fragments went. And so what does the photoelectron angular distribution look like in the recoil frame as compared to the molecular frame? And finally, I'll talk a little, so that'd be for linear molecules, it's quite simple. For nonlinear molecules, things are a little more complicated. You've got another angle to worry about. And finally, then I'll talk a little bit about something called rescattering spectroscopy, which gets at some of the same sort of information, but rescattering spectroscopy is when you have high field ionization, the electron comes back out and then rescatters off the ions. It's a way of getting that electron-ion scattering using high field lasers. Okay, so molecular frame for electron angular distribution. So if you have your coordinate system, and let's say the molecule for a linear molecule is aligned along the z-axis, then there are basically three angles, or four angles. You have the electron, the direction of the field orientation, this end. So for linear polarized light, you'd have the direction of polarization. If it's circularly polarized, the direction of propagation. If it's elliptical polarized, then there's another angle, but let's not worry about that. Then you have the two angles for the electron. So in general, you might write the intensity for the photoionization and the function of these four angles, the spherical harmonic expansion, and you get some coefficients. Okay, that's the way a theoretician would approach this problem. Now experimentalists, they like to think about what's the best way to analyze this data. And so one of the first things I did when I started this collaboration with Daniel Dweck in Paris was to say, well, let's try to simplify the equations a little bit so that experimentalists have some tools to work with. And so first of all, if you consider just linear molecules and one photon ionization, then the sum of the circular harmonics on the field then only go up to L equal 2. Okay, so that certainly simplifies it. And then you can rewrite this sum in terms of four one-dimensional functions, which tell you what the dependence of the electron emission is relative to the molecular axis. And then all the field terms you can factor out in these low-order polynomials. Okay, so basically, experimentally, if you're doing photoionization of a molecule, there are only four one-dimensional functions which characterize the angular distribution of the photoelectron in the field of that molecule. And so you can take this 4 pi collection data, get all this data, and reduce it down to four one-dimensional functions. And once you have these four functions, then you could predict any possible combination of the orientation, field, and the intensity for the photoelectron going in particular directions. So once we had sort of analyzed, this is fairly simple-minded, don't you sort of realize you only need these four functions, then you can take all this data that they were collecting and reduce it down to some useful information. The other interesting thing was, well, that was for linearly polarized light. What about circularly polarized light? Well, for circularly polarized light, you have the exact same 4 functions, with one more having to do with the helicity of the light. Okay, so actually in a single circularly polarized light experiment, you could extract out all 5 of these functions and get all the possible results. Be able to totally encapsulate the experimental possibilities. And when you go to elliptical polarized light, it's basically the same 5 F functions with this other angle in there. Okay. Now, so qualitatively, what do you expect for the molecular frame angular distribution? So it's basically based on the square of a dipole matrix element. You have some initial state, dipole operator, continuum. So clearly, you're going to have contributions both to the initial state and the continuum. Now, for simple diatomic systems, for valence ionization, fairly low energy, then you can extract out some of the important parts of this dipole matrix element. So the one important part is the fact that this continuum here is a Coulomb wave. And there's a Coulomb phase shift, this sigma Sibel, which really dominates a lot of the angular distribution information. So it controls the interference between S waves and P waves, or S waves and D waves. So that's a big piece of what's going on. Just getting the Coulomb phase right gives you the interference and the angular distribution of the partial waves. On top of that, then, there's some scattering phase shifts. So fairly near threshold, these scattering phase shifts are actually connected to quantum defects, of course. And so typically for a small diatomic, N2CO, even CO2, you sort of qualitatively know ahead of time on the order of magnitude how big those quantum defects are. And so for S sigma, it's a fairly large quantum defect coming from how the Rydbergs are shifted. For P sigma or P pi, the quantum defect is about 0.7, D sigma 0.2, and the higher angular momentum typically isn't much in the way of quantum defects. So if you just assume some fixed quantum defects and you ignore the energy dependence of the radial part of the integral, you can actually then predict qualitatively what these fairly low kinetic energy angular distributions should look like. So I'll give a few examples: S sigma, P sigma, P pi, and so forth. Okay, so if you're ionized from a 1s, okay, where is the photoelectron going to go? So for 1s, the only information is given by the field, and so the angular distribution then is actually oriented along the field. So if it's parallel, well, for the 1s, there's no parallel and perpendicular anyway. So along the molecular axis, if you're coming from just like the core 1s, you just get sort of a p squared kind of picture. If you had some angle, like the magic angle, it's just rotated and perpendicular to rotated again. So the 1s then, clearly, it just follows the field. Okay, now what happens if you're ionizing from the p sigmas? This would be like the p orbital along the molecular axis, or in hydrogen be the 1s, the antibonding combination of the 1s or the 2s orbitals. So in there, again, along the axis, you get this fixed, the intensity is strongest along the axis, and then as you bend, it follows it to some extent. But now when you get perpendicular, you're coming from p times a p, you get a d function, right? So you see something that looks, at least in the square and the intensity, it looks sort of like a p orbital. Well, it's got a lot of d and s combination, but perpendicular, it looks very d-like. So just from these pictures, then if you can expect, know sort of what to expect. Well, typically for a molecule like CO, or I'll look at example NO, then you don't have pure S or P, you have some linear combination of the two, you break the GU symmetry. And so this is from a simple SP hybrid, then you can get these very intensities directed in a fixed direction. So again, you have a linear combination of a number of partial waves, so it has different energies, this will change. But you can see these kind of pictures as a function of the orientation of the light relative to the molecular axis. And one final one is this L equal coming from a p pi. This would be like from the pi orbital in N2, for example, or the inner pi's in O2. So from a p pi, then you again, if the light's parallel, you get this sort of d orbital, but it's rotated. I mean, it's got this like a figure of rotation. And then here, the field going this way, actually the intensity goes up perpendicular to that. Now the interesting thing is that as you change the kinetic energy of the electron, this thing can change quite a bit. And this is really just coming from the fact this is an interference of L equals 0 and L equals 2, and between 1 volt and 20 volts, the Coulomb phase changes a lot. Okay, the relative phase between D and S changes quite a bit. So you can get strong energy dependence in these angular distributions based on these simple Coulomb phase shifts. So it's a kind of picture that you'd expect looking at the valence ionization from diatomics or triatomics. Okay, so the group that I actually directly collaborated with is this group of Daniel Dept. And so it's very similar to like a Coultrim's experiment. They have the molecules, supersonic jet crossed with a beam, either laser or synchrotron in this case. And then if you have dissociative ionization, then you can accelerate, which way is it? The electron down here. So you accelerate the ion up, and the electrons would be accelerated down, and use the right ion optics, you can collect, for not too high kinetic energy electron, you can collect electrons in all four pi directions. So the combination of the timed light source and the time of flight and the position sensitive detector, then you can measure where the electron was going, where the field was. You don't really know where the field was, where the electron and the fragment went. And so if you assume then that this molecule fragments quickly, so the molecular axis is the same axis as the recoil fragments, then you can experimentally get the molecular frame angular distribution. Okay, so one of the first molecules we looked at was the ionization of NO. Now, to get to a state, so this coincidence experiment depends upon doing a dissociative photoionization. So you have to go to a state which is going to fragment. Okay, so the first state that fragments is this C triplet pi state. It's fairly far up in the manifold of ion states. And so, anyway, so that's the C triplet pi, which is basically ionizing from the 5 sigma orbital NO. And the theory then, we could then calculate these MF pads and compare with the experiments. And the experiment, the agreement's relatively good. So you can see this looks sort of like a d orbital, and this is very much d orbital-like. But the fact there's some asymmetry here, just telling you that it's really not pure, sp hybrid. You got some combinations there. And so actually, what we did in this case is we then sort of dissected the calculation a little bit to see. Oh, I'll get to that in a second. So those beautiful pictures then can sort of hide a lot of sin, so to speak. And so let's actually look at the F function. Sorry, wrong direction. So these are these 4 F functions that describe the angular distribution for linearly polarized light. So the red line is the theory, just a fixed molecular theory. Then there's a convolution with the apparatus function, basically the fact that there's some finite resolution in the detection times and the finite interaction volume. So going from the actual fixed molecular frame to including these experimental effects, then we can actually get fairly good agreement with dream theory experiment. But these 4 functions for linear polarized light tell the whole story. Once you have these functions, you know everything about the MF pad in these systems. Okay, so what determines those pictures in this particular case? It actually was a fair amount of correlation was needed to get these to agree with the experiment. So there are different kinds of correlation. One would be like static correlation, where they actually have the correlated target. Okay. Then there's dynamic correlation, where the target is responding to the incoming or the outgoing photoelectron. And the way we just basically do close coupling calculation. We include various ion states to include this dynamic correlation in the system. And at large distance, the electron is going to feel just the polarizability of the target. But for photoionization, the Coulomb potential means that those typical polarizability terms aren't so important. Okay, so here's NO, the 5 sigma, the 1 pi 4th, 2 pi. So this is the doublet pi to your ground state. And then you can make a bunch of ion states. And so this C state, which is dissociative, is up here at 22 volt ionization potential, or 22 volts. And so what we did is we did different calculations, including different sets of ion states. So we do a close coupling calculation with I think the first one, you can just do one channel, then 5 channels of the red ones plus the purple one. And these are just the sigma holes, and then we did a larger calculation where we included all the different pi hole states and some important higher states. So looking at these different calculations, the one channel, which still has a correlated target, but has no dynamic correlation in the scattering, basically doesn't get this picture at all, right? Okay. And so, but putting in the sigma hole states in the 5-channel calculation, then got the polarizability of the molecule along the axis better, and that agreed pretty well with the experiment. In the perpendicular direction, those sigma hole states didn't do anything, but when you include the pi hole states, then the ionization in the perpendicular direction looks a lot like the experiment. So even though these, in the end, look fairly simple, d orbitals, different d orbitals, actually to get them to come out of the calculation took a lot of dynamic correlation in the system. Okay, so 17-channel calculation had the pi states, and you've got the perpendicular polarization better. Okay, if you go to high energy, this other one, the first one was at 25 volts. That's just basically like 4 volts above threshold. If you go to high energy, 40 volts, these dynamic correlations are a lot less important. Going from 1, 5 to 17 channels, it changes a little bit, but the main features stay the same, and the same for the perpendicular and the magic angle. Or there's actually circular polarized line. So at 40 volts, there's not much, the correlation effects are fairly small, and you get the strong preference for the ionization going down. Okay, so that would be, all those calculations assume that the molecule was fixed in space, ionization occurred, and the molecule fragmented in the same direction. Now, so this basically is what's called the axial recoil proxy, assuming that the molecular bond that breaks tells you the direction of the fragmentation. Okay, so what happens when that fails? So for linear molecules, one thing that can happen is the electron can leave the system, and it can take a little while for it to fragment, and so the system can rotate and then fragment. Or even for linear molecules that are polyatomic, triatomics, molecule, then you can ionize and you can have some bending dynamics before it fragments. So your recoil direction doesn't necessarily have to be the same as the original molecular axis at the time of ionization. Okay, and then for nonlinear molecules, if you only measure 2 fragments, by definition, you don't know what that third angle is. So you're always getting the recoil frame distribution. Okay, so here's the effects of rotation. So you start out with the molecular axis, and the ionization event occurs, the electron leaves, has some time to rotate before it dissociates, perhaps. And then the recoil axis, the angle relative to the recoil axis is different than the angle relative to the original molecular axis. So you have to take your molecular frame angular distribution, and basically you can do a calculation, including the temperature of the beam and all those effects to give the distribution of recoil directions relative to the original direction. Okay, and so we studied this on this system, on this O2 ionization, where you ionize to this state up here, this double sigma G minus, and it actually is slowly dissociating down to this curve here before it fragments. And that takes about a half a picosecond. Okay, and so again, we can calculate the fixed molecular frame angular distribution. You can put in the instrument function, and then you can put in the fact that it has a rotation time. And so the agreement actually is quite good now when you put in this half a picosecond rotation time. So even though you would think that once you break the recoil, axial recoil approximation, you lose all hope of using this approach, there's still quite a bit of information in certain of these functions about the original molecular frame. You don't lose all information, even if it takes some time for it to rotate. Okay, so about bending. So you start with a triatomic, ionize the system, it can bend, and then the fragmentation, the recoil direction is different from the original axis, and again you have this rotation of the system that you have to include. And so this is one example we did for N2O, and so the solid line is the original molecular frame, and then if you put in a bending angle of about 30 degrees, then actually degrees, this has to do with circular polarized light. You can see there's quite a bit better agreement for that feature. Okay, so you can actually use this as a way of extracting something about the lifetime of the ionization. How long did it take? How closely does the molecular frame angular distribution you measure compared to the original molecular frame. And from that, you can learn something about lifetimes of these ion states. Okay, so what about nonlinear systems? So nonlinear systems, one thing you don't have is the quantum number for motion about the molecular axis is no longer fixed quantum. I mean, no longer a good quantum number in that sense. And so you get many more terms in these sums. And if you have a system with some symmetry, you can get a reduction of that. You only get n plus 3, but you still have a lot of terms to consider. However, if you don't measure, so with a nonlinear molecule, you have say the recoil axis, and then you have this unmeasured gamma angle. Okay, and so if you actually take the intensity and average about that unmeasured molecular orientation angle, you recover cylindrical symmetry, basically, and so you end up with the same 4F functions. So you can analyze the recoil frame for dissociative photoionization for nonlinear systems in exactly the same way you did for diatomics or linear molecules. Okay. So we did some studies on methyl chloride. So there are lots of different channels for fragmentation. This is for ionization from the chlorine 2p up here, and it can fragment various different ways. And we analyze, if you only get 2 fragment channels, all you get is the recoil direction. And there is some of this channel where you get all 3, and you, in principle, can orient it. But the experiment didn't have enough intensity, really, to figure that, to see much in that channel. But I think we just looked at this predominant channel up here, the CH3 plus fragment, Cl plus. There's some issues having to do with the spin orbit states, which we ignore, and we basically adding them together. But the angular distribution is the same basically for each spin orbit state. Okay, so you have these 3 different p orbitals. So you have the pz along this carbon-chlorine bond, and then you have the 2 perpendicular ones. And so if you add all 3 of these together in the molecular frame, this is what you'd expect. And then in the recoil frame, where you don't measure the orientation of the hydrogens, then you get these cylindrically, this one, at least the parallel one is cylindrically symmetrical, and you get these simpler MF pads, and the other orientation is y relative to the axis. Okay, then we can compare experiment and theory, and they look pretty good. So for the parallel, we don't get everything 100% right. These are fairly simple calculations. This is basically Hartree-Fock-like scattering calculations. But you can get pretty good agreement between the theory and experiment for these 2p ionization of methyl chloride. Okay, last thing I wanted to talk about briefly is a related topic in the sense that it's looking at electron-ion scattering in the molecular frame. And so what actually, there are a number of theories associated with high harmonic generation. Basically, you have tunnel ionization, the electron in a high field, the electron can tunnel out, and then it can be accelerated out and back, and then recombine. So in high harmonic generation, then you actually have the dipole matrix element. You have the returning flux and the dipole matrix element here. And so we've actually done some studies looking at the high harmonic generation. But what I want to talk about today was not that, but looking at the electron scattering part. So nothing that can happen, this electron coming back, doesn't have to be reabsorbed, it can also be rescattered. And so if you detect where that electron is scattered to, and if you know something about the orientation of the molecule, then you can actually extract out electron-ion angular molecular frame electron-ion scattering. Okay, that's called, this is the work I've been doing in collaboration with Kiyoshi Ueda, and they refer to it as rescattering photoelectron spectroscopy. I guess you've got to have a catchy name for every effect. Anyway, so let's look at this rescattering electrons from ions and the electrons are being produced from high field. And in their experiments, they didn't actually pre-align the molecule. You can imagine doing impulsive alignment of the molecule and then do the high harmonic generation of the ionization and rescattering. But what they use is the fact that this first step, the tunnel ionization, actually depends on the molecular orbital you're coming out of. So you can get some partial alignment based on the fact that on which direction the orbital is pointed. Okay, and so we looked at CO2, look at the pi g orbital, and C2H4 from the pi u. And they use a range of intensities, different pulse lengths, and the main connection between what I can calculate, I'm just doing field-free electron-ion scattering, molecular ion scattering, is that when the electron comes back, usually, depending on the length of the trajectory, it may or may not have any field present. But the highest energy electrons, for a given field strength and pulse duration, the highest energy electrons that are rescattered, those are the ones that arrive in field-free conditions. Because if any field present, then they were, by definition, aren't going to be the highest energy electrons produced in a particular set of particular conditions. So if you look at the highest energy electrons for a given set of conditions, they actually arrive under field-free conditions. So the idea was maybe by looking at those electrons, then you could get the field-free electron-ion scattering distributions. Okay, so here is a typical rescattering for electron spectroscopy diagram. This is actually from CO2, and so this is the momentum, px, pz, and the intensity given in the color. And so, so what you first thing you see that there, once the electron leaves the system, so this electron, once it's been rescattered, will still feel the field. So you get this Ponner motive shift. So you get a Ponner motive shift of the kinetic energy, and so you can determine then what the momentum was when it originally rescattered, and from that you can then extract out the angular distribution of the rescattered electrons for a given momentum of the electrons. Okay, so in C2H4, then the first thing you needed would be to calculate the ionization rate as a function of angle. So in C2H4, this is the ionization as a function of where the electron goes, and it's strongest when you're perpendicular to the axis, 90 degrees, and so it's coming out of the pi orbital and mostly being ionized this way. So you get some orientation. You don't have this other angle, but the fairly strongly peak perpendicular to the axis. So you get some orientation. So when you average over all the different emission angles, since it's fairly strongly peaked in the perpendicular direction, you get some orientation information about the molecular orientation. And so here is the scatter. So for Coulomb scattering, obviously forward scattering is dominated by the Coulomb part of the potential. So you look at the back scattering, 90 to 180 degrees, and then this is a function of the momentum of the electron. So this is what we calculate, and this is what they measure. And so you see this prominent backscatter peak, but there's also some evidence here of a peak around 120 degrees. And then here you can see the computed angular distributions for given momenta. So here the red circles are computed, and then there are different experiments coming from different intensities of light. So here, this one, P equals 1 atomic unit, agrees pretty well. Let's see, look at like this one here. So here's the computed, and then they have results from two different experiments. One from 7, I guess it's 10 to the 14th watts per square centimeter. And so the lower, so for given momentum, the one that's generated at lowest field actually agrees better with the experiment. Go to higher field, that means for a higher intensity light, then this is not occurring, it's not its highest momentum that you can generate. So these lighter blue circles then correspond to experiments where you're not at this extreme limit of the rescattered momentum. And similar down here, at the higher intensity light for the same momentum, the agreement's a lot worse than for the lower intensity light. So by picking out only the highest momentum for a given intensity, then you can see you're getting close to the electron ion rescattering, scattering from the molecular ion. And this peak at 120, so remember this is back scattering, so the red line here is the direction of the electron coming back, and so when this is at 60 degrees, let's see, so if theta is at 60, then that would lead to, so you get sort of pseudo-specular scattering here, like this one here. So here's the beam coming in, you get a big peak going out this direction, And so that's actually at 120 degrees from the original, from the rescattered direction. Okay. So you get the strong peak, which is actually coming, from the sense, from specular scattering off this, if this were like a plane. Okay. And so you can get some structural features using this. Now, of course, the way people sell even being interested in this is to say, well, if I can go to much higher energy, so if I can go to longer wavelength, have a much higher rescattered energy, but the 100, 200 EV, then you'll start seeing more like diffractive scattering. But even at a momentum of 1, that's 1 atomic unit. So that's not very much energy. Right? 1 atomic unit was a half, right? 13 EV. Hartree. 13 EV, right? Yeah. So these aren't that high of energy. So so the current experiments, they don't go that high, but in principle you can go to longer wavelength to higher energies, and you begin to see something that looks a little more diffractive. Maybe you could measure the structure, those kind of things, that kind of idea. Okay, so a couple points, and one is that for doing the single photon ionization, these FLN functions are the best way to analyze the molecular frame information. So you get 4 one-dimensional functions, gives you all the features. Even when the axial recoil approximation breaks down, these experiments based on coincidence measurements can still give you quite a bit of information about the molecular frame ionization. Again, for nonlinear molecules, if you just look at 2 fragments, you again get the simple FLN expressions. And the rescattering spectroscopy accesses related information. I mean, it's electron ion scattering, and you get some molecular frame information. Now, certainly, if you already really, impulsively align the molecule, you'd get more molecular frame information. But even just using the angular dependence of the tunnel ionization, you can get some molecular frame information in the electron ion scattering. So that's all I'll talk about. Thank you for your attention.
Chris, when you're looking at these rescattered electrons coming back in, you are interested in the one that's coming in with lowest energy, correct?
For given laser conditions, it's actually the highest one. So one that's at the edges, right at the. I mean, if you look at the spectrum of electrons, right, it has this plateau and then drops off. It's the one right before you get the drop off. The end of the plateau is the one that returns to the molecule when there's least field.
What's the typical energy with that electron to which it has been accelerating
Well,
way back?
Well, I mean, in high harmonic generation, they typically, get the 51st harmonic or something. You're talking about 50 volts, 60 volts, 70 volts.
And I've always asked this question. Doesn't that electron whack that ion pretty hard? And they seem to make the assumption that that ion is sitting there doing nothing, just scattering. I mean, this is not on you, but every time I hear these guys talk, this question arises in my mind.
Right. So if you scattered, 50 electrons from a neutral molecule, right? There's some ionization cross section.
Right.
There's still a lot of elastic collisions, right?
That's right.
In fact, usually excitation and ionization are pretty small, right?
But based on the success of the model, yes, that has to somehow be true.
Right.
It always amazes me. The quick question before I give up the floor. On the laser alignment that you referred to, I mean, if you, for diatomic, that's going to be nice, right? It's easy. You can align them on that axis. But if you go to a polyatomic,
right. Well, you need.
It's going to be tough to get alignment.
Right. If you need a molecule with 3 different, polarizability tensors.
Right.
And these experimentalists claim, well, first, one problem is you don't get this nice recurrence in the rotational wave packet, right? So you only get partial recurrences based on whether you get 2 axes that are similar to each other, whatever it is, right? I mean, Tamar Seidemann talks about this all the time.
Yeah.
But even for diatomics, the angular spread is actually, not that narrow. I mean, I did some comparisons to some, work Mark Fracking has done, and, their distributions, 20, 30, 40 degrees, even for the best experiment.
It's almost 20 degrees
away from that direction. So they're fairly broad, even in the diatomic.
Okay, that's helpful. Thank you.
I was wondering, I mean, the examples you showed, the theory is working really well, but my impression is that there are a lot of problems where we need better technology to solve the electron-molecule interaction. And would you say that's at lower energy, where polarization effects are more important than the regions you're looking at? Or, I mean, what are the main things you'd like to see your own codes improve?
Well, so first of all, one reason why these ion calculations work pretty well is because there's the Coulomb potential. So polarization, it's there, but it's not so important. Okay, but you can see for NO, 15, 17 channels before you really got something that looked like the experiment. And so it really depends on what you're looking for, right? I mean, if you're really, for my codes, I'd like to be able to do, so like we're doing harmonic generation from SF6, okay? And so one question then be, what about the interchannel coupling? I mean, you can see resonance as one channel. Does it affect the harmonic generation in a different channel? And then you'd like to say, well, what happens, modify the code to put in some effects of the field. Can you do the scattering with an external field present or some approximation to it? So as people are looking at bigger systems, it'd certainly be interesting to be able to do some of those correlation and coupled channels and correlated targets that we can do for small systems.
Yep.
Well, I have a short comment and then a question. The comment is that the photoionization and the high harmonics are two competitive processes. And in the case that you take the high harmonic generation, in a way it's misleading to think that the electron is ionized and somehow the field brings it back. It is never really a free electron. What you have is a metastable state, what we call resonance. And the high harmonics are generated by neutral atoms, and not by an ion or something like this. And this description that you described with the three-step model, this description is very helpful to visualize what's happened in the experiment, but it's limited to the low-frequency regime. Like I assume that you use titanium sapphire or something like this. If you go, and this is the question actually, can you really go and somehow, I don't know how far, you can go to the high-frequency regime, namely to use not the fundamental frequency photon that you have, but you use the second harmonic as a source, or the higher harmonic as a source, because then I expect that for high-frequency enough source, you will see the breakdown of the agreement between experiment and theory. Because,
I agree.
So can you do something like this? Can you repeat on this experiment with?
Well, first of all, I'm a theoretician, so I can do the experiment. But in fact, the experimentals are headed in the other direction. I want to go to longer and longer wavelength, low frequency, because it gives access to higher kinetic energy of the rescattered electron and higher photon.
What about going to higher?
They're not going to higher. And one part of the reason is, what you're suggesting is that the theory for that is more difficult to understand.
Well, since I know this theory, this is why I'm asking you.
Okay, why don't we thank Robert again.